So welcome to lecture 25 of our CS6 CS2 classes. And I think today we're going to discuss about the forecasting of ARIMA processes. And we'll look at something else, which is just a different method of forecasting the processes, apart from the one that we have studied as yet, which is Box-Jenkins. And we did not always use this complex method, to forecast. Sometimes it's really easy, and we'll see what that easier method is. And then we will have a look at something that we can do with non-stationary time series. So there is one exception to, be able to try and understand the non-stationary time series and try to model them together. So we'll have a look at that, and then we'll also try to have a look at other non-linear and non-stationary models which are prevalent in practice but not discussed within the purview of our syllabus, and we'll end off with a sum from the exam style questions. So let me just start my screen sharing. Okay. So just to remind you all about, the techniques that we studied about removing linear trend from the data. So the first was least square trend removal. Then we know that sometimes that is not enough. So you have to use differencing as well. So that was another method. Then we saw what to do if there is seasonality in the data. So instead of normal differencing, you can use seasonal differencing, where you write this subscript 12 here. So if you write this nabla 12 xt, what you get is xt minus 12. So the next method was method of seasonal means, where you try to, average out the effect of all of these variables. And the last one was method of moving averages. So these were the methods used for removing a linear trend. And if you, let's say, have a non-linear trend, you can resort to either the transformation of the data, or you can use this variance stabilizing transformation, which could lead to something, the same conclusion as this. And the last was just to transform the data so as to increase its normality. And because we know that we can only work with the models, the forecasting models that we have, if the error terms are normal. So we want to make sure that the error terms that we have are normal. So once we have made sure that our time series at hand is a stationary process, then what we do is we identify what kind of a process it is. So depending on the ACF and the PACF, we determine whether it's a white noise, AR, or a MA model. And if not any one of these, then you resort to Box-Jenkins method, where you assume that, so initially you assume that the model is ARIMA, and once you have removed the stationarity, the integrated factor is removed, and then you are left with ARIMA model. And then you figure out the parameters of ARIMA P, Q model. And once you figure out those parameters, you essentially see that the model that you have fit, is it a good model or not? So, or let's say if you have fit more than one model, then you can compare those models and their performance using these techniques. So one of it is to check whether the error term is normal or not. And you can use a graph, or you can use SACF, or you can even use the counting turning point method to realize if the error terms that you have are indeed a white noise process or not. And next up, we looked at, the forecasting part of it. How do we write it in terms of this, essentially the hats and all this sort of stuff. So the very first step we do is we replace all the unknown parameters that we have, which are mu, alpha, and beta in the ARIMA 1,1 case that we are looking at now. So you replace them with the hats. Then you replace all the known values, which are the observed values of xt, with their realizations. And the next step is to replace the random variables which you do not know as yet by their forecast values. So if you have xt plus 1 and you only know values up until time t, what you can write is xt and in bracket 1, which reveals that the variable that you're looking at here is xt one step ahead. So xt plus 1. And then again, you replace all the innovations that you know up until now by the values that they have realized. So you just put a hat upon the variable. And the random variables which you haven't yet observed, the error terms, you replace by their expected values, which is of course 0, because you assume that the error terms are 0 mean white noise process. So you have to take that into consideration. And I think the next thing that we had a look was that you generally not resort to point estimates of ARIMA, but you try to have a you try to have a horizon of forecasts which will guide you or give you a prediction interval so as to guide which values the variable can take at minimum and at maximum. So you just increase your confidence about, the variable lying in between that interval, rather than giving just a point estimate, which might be either 0% correct or 100% correct. So now today we are going to look at, a way. So let's say if I give you guys ARIMA model. So I think we have already discussed this before. So let's say I give you a ARIMA model, which is something like 0, 1, 1. So I know that this has to be integrated once for it to become a stationary model, because let's say if I have xt here, I know it does not depend on xt minus 1, but it does depend on at minus 1. And also I know that it is an integrated process of order 1. So if I difference this process one time, then I will get something which is a stationary model. So let's say I difference this once, and what I will get now is a ARIMA model with parameters like this, right? Because there is only one. So if I difference it once, I should get something which is a stationary model. So now when I write this, I know the D being 0 here just says to me that this model is already a stationary model. So maybe just to rewrite and see how do you derive the values. So I know that the forecasting methods, the Box-Jenkins method that we just studied, can only be used if we have a stationary process or a stationary series, right? So I know that I cannot use my Box-Jenkins directly on this. So what I'll do is I'll difference it once, and the data set that I have now, I'll use and forecast the values for this. So let us see that I have my variable xt and I have differenced it once. And after differencing it once, I define a zt, which is just, the difference xt. So it is just going to be xt minus 1. And basically, if I'm writing ARIMA 0, 0, 1, so I know that my zt is nothing but ARIMA 0, 1, right? So I have this model, which is a stationary model. And now what I can do is, I can forecast the values for zt now. But what I need in actual is the values for xt plus 1, xt plus 2, not zt plus 1 or zt plus 2. So what I do is, I reverse the process, I back engineer, and what I will do is, I will rewrite this expression here. So we can reverse difference and get the value for xt. So if I have to write my value for xt here, what I will get is xt minus 1 plus zt, right? And I know that having t plus 1 instead of t, I can easily write my xt plus 1 as xt plus zt plus 1. So my zt being a stationary process, I can forecast its value, which will be zt plus 1, which will be the value that this random variable will take. And then I know my today's observation. And by using both of these, I can predict what's likely to be the value of my variable tomorrow. And if I have to rewrite this in terms of the forecast or the realized values for this, I will write xt plus 1 as xt 1 hat. So this is my small xt, which will be equal to today's value, which is xt. And then I have this. So this is zt plus 1. So this is again my forecasted value of zt with time step 1. So this is how I can write my forecasts if my actual process is ARIMA. Is this clear?
Yes.
Okay. Any doubts in this? So with any, how to write these equations or anything basically, I think we can solve a question to, make this reverse difference and just the way to write forecasts much more clear. So let me do an example. So let us say I want to write a 2-step ahead forecast. For an ARIMA model with 1P, 2D and 1Q. So would anyone want to try this on their own? Anyone? So what is the D here? So the D is 2. And I know that I will have to difference my time series 2 times for me to be able to get to a stationary series with which I will forecast, right? So if I'm defining the variable which I'm going to forecast or the series which I might be able to forecast as Zn. So let me define as Zn the variable or the series that I can forecast. So I can rewrite it in terms of, so if I have to rewrite it in terms of x, how should I write it? So I have to difference it 2 times. Anyone? How can I write my z in terms of x? So remember, z is the process which has to be stationary. Anyone? So remember, in the previous case, what I did was I had a series which had to be differentiated once for me to get to a stationary series. So I wrote my zt as nabla xt. But now if I know that, I will have to difference my series twice. How can I write my Zn as?
Delta square xt.
Exactly right. I will have to write it as delta square xt. So I know if I difference my xt twice, I'm going to get a series which is a stationary series. Again, I can, if I have to, so this is just the start of the process. I know I haven't yet written my Zn in terms of x. So probably I should just write xn, stick to the same. Okay.
Here
So,
xn follows ARIMA 1-to-1.
yeah, here xn follows ARIMA 1-to-1 and Zn will probably follow ARIMA 1, 1. But let us see what happens. So if I have to rewrite my Z in terms of x's, what I can do is I can substitute instead of this nabla square, I can write it as 1 minus b square xn. And when I expand this 1 minus b square, what I get is 1 minus 2b plus b square xn, which will be translated to xn minus 2, b times xn will be xn minus 1 plus b square xn will be what? So b square xn will be b times bxn And my bxn is what? Xn minus 1. And my b of xn minus 1 is just xn minus 2. So I don't even think you guys should have to write this. I mean, you can directly write it here that it's going to be xn minus 2. So now again, remember the next step is to write the expression, the variable that I care for in terms of all the other variables that I know. So again, we care for the xn term here. So I will rewrite this in terms of xn. And what I started off with was zn. So if I have to write xn, that will be equal to zn plus 2 times xn minus 1 minus xn minus 2, right? Now what you have to consider is, look at what kind of forecast do you care for. So here they have asked us to carry out a 2-step ahead forecast. So if I am currently at xn, what I have to figure out is what's going to happen at xn plus 2, because I have to look at a 2-step ahead forecast, right? So if I were to rewrite this expression using n plus 2 instead of n, what will I have? I will have z n plus 2 plus 2 times x n minus 1 plus 2, which will be n plus 1, and minus of xn. Is this clear to everyone?
Yes, ma'am.
So this should be my answer, right? Or no? So remember, you never stop here, because what they have asked you is a forecast. And remember how we write forecasts? You have to put hat on the variables that you already know and leave the rest of the variables with their expected values and the forecasts with the time step written in the bracket. So now if I have to rewrite this as a forecast, what will I write? I'll write the realized value of my xn, which is xn hat, and 2 time steps ahead, which will be equal to, I have zn plus 2. So let us leave this at the end and rewrite this first. So I have 2xn plus 1. So I'll write 2, again x hat n in bracket 1 minus xn. This will be as it is, right? This xn will be as it is. And now what you will do is, because this is the one which you have observed, so remember, I will never put a hat here because I have observed my values till n period of time. But for any time step which is ahead of n, I have to forecast. I have estimated a value, and because I'm looking at its estimator, not the actual value, you have a hat over there and no hat over here. So this is very important. And the last is this term from here. So this will be Zn hat with 2, right? So now if I just put in some assumption, now if I tell you to assume that my Zn is just mu plus alpha times Zn minus 1 minus mu. So now I have given you some additional information about my Zn, right? So what do you guys think will happen to the Zn plus 2's realization, which I have written here? Would someone like to help me to write that out? So I know that these values will be as it is. So I just have to figure out this, right? So the very first step should be what? What should be my first step to figure out the forecasted value of my Z 2 time steps ahead when I'm starting at N? Anyone?
Writing the equation for Zn plus 2.
Right. I should write my equation for Zn plus 2. So if I start writing my equation for Zn plus 2, let's see what I get. So now I'm writing my equation for Zn plus 2. The mu will be as it is. It does not depend on time. Alpha doesn't depend on time. And instead of n minus 1, now I will have n minus 1 plus 2, which is n plus 1. So let me just write this z as this because otherwise it gets confused with 2. So minus mu plus e n plus 2 plus beta e n plus 1, right? And now what I have to write is the forecasted value. So I know that I should put a hat on all of these estimated parameters. And this is my forecasted value again. So this will just be written as Zn hat 1 minus mu will be written as its estimated value. And now I have En plus 2 and beta En plus 1. And I know that this will just be 0 because the expected values of e's after n are always going to be 0. So my Zn hat 2 takes this value. And for the final answer, what you will write now is, assuming that this information was provided to you, you can write that your xn2 is 2xn hat 1 minus xn plus, and instead of this Zn hat 2, you will write this expression here. So it will just be this. Is this clear to everyone?
Yes.
Okay, so I think that would be it about writing the forecasts, you know. So you haven't yet forecasted, you just have to know how to write this forecasts. And then you can use the method which we studied in Box Jenkins and write the values, the actual values for mu, alpha, and all these other variables that you get. Now let us try to study what happens if I do not have the resources. Let's say you don't have these very able statisticians who know this Box Jenkins methodology, or sometimes you need not, you know, have all of these complex processes for forecasting. And the rule of thumb technique generally is to resort to exponential smoothing. So this is another type of forecasting technique that you can use, and which doesn't require much of, you know, careful estimations of parameters and all of those stuff as in Box Jenkins. So let me just write. So yeah, so what happens in exponential smoothing is you provide the past values some weight to predict the future observation, and that weight is not random. That weight is already determined from the beginning. So again, if I were to write my forecast one step ahead, what will you write it as if you are exploiting exponential smoothing? Will be something like this. So you have alpha here, and that will be the weight to the past observation, which was xn, and then you decrease your weight. So again, I'm going to assume that my alpha value is between 0 and 1, because I expect that my dependency of forecasted value one step ahead decreases as in when I increase the lagged values. So I'll have 1 minus alpha for xn minus 1, and then I'll have 1 minus alpha square for xn minus 2, and so on. So the bracket should also be completed, and that is how you do exponential smoothing. So if I were to write this in a condensed form, what I can write it as alpha, and then I will just sum it across 1 minus alpha raised to I. So I know when I raise to 0, I get xn. So this will just be xn minus I, and I goes from 0 till infinite. And essentially, what you see here is, if I increase my value of alpha, let's say if I have a large value for alpha, then I can clearly say that my 1 minus alpha is going to take a lower value, and 1 minus alpha square is going to take an even lower value. So if I have a large alpha value, then I'm looking at a model which pays attention lesser and lesser, as in when you look at higher lags. But sometimes if you have a very small value of alpha, what happens is you want to take into consideration more of the history to make a prediction. And that might be useful for some cases, but may not be useful for other cases. And the discretion is upon the statistician to decide and gauge what kind of value you should have for alpha, depending on the kind of time series that you're looking at. So, and again, I think when I'm calling these coefficients to Xn as weights, I mean that all of those, if you sum across till infinity, will sum to 1. So let us see what happens if I were to sum this up. So I will just write the sum of weights. And what I'm looking at is alpha, and then I have summation 1 minus alpha raised to I, where I goes from 0 to infinity. What should I write here? How can I expand this sum as? So alpha will be as it is. And what will this be? So you will have to use the geometric progressions formula of infinite sum, which is what?
A upon 1 minus R.
Exactly right. It is A upon 1 minus R. So here my A is what? Here my A is 1 minus alpha raised to 0. And 1 minus R. R is just 1 minus alpha. So what will I get? Let's see. So I have alpha, that will just be 1 upon 1 minus 1 plus alpha. This is 1, right? So this is indeed a linear sum of weights, right? Because they add up to 1, and it's a really nice exponential smoothing that you've got there. So, yeah. And as we see, this is something which will also help you to forecast. But how does it help you to forecast? So let us see what happens if I expand this brackets and if I take some terms out of the brackets. So what I have here is x hat n 1, and I'm trying to forecast one step ahead of xn. So what I have here is alpha xn. I'll rewrite that, and I'll write my alpha here again. So I just took this term out of the bracket, and I'm writing all of the rest of the terms again here. So I have alpha 1 minus alpha, and then in bracket xn minus 1 plus 1 minus alpha xn minus 2, and so on. So if you see what I did, I took this alpha common again. So I had alpha times 1 minus alpha for xn minus 1. And again here, if I see my coefficient for xn minus 1, I have alpha and 1 minus alpha. And for xn minus 2, I had alpha times 1 minus alpha square. So again, if I'm taking alpha and 1 minus alpha common, I will only have left 1 minus alpha here for xn minus 2, and so on. So now, if I look at this right here, and if I take this 1 minus alpha common, so I'm taking this 1 minus alpha as common, and I'm writing the rest of the terms as it is. So I have alpha times xn minus 1 plus 1 minus alpha xn minus 2, and so on. And if I have a nice look at what I got here, I can see that this is equivalent to xn minus 1 hat 1, right? So if I put here instead of n minus 1, what will I get? Alpha. And here I'll have n minus 1. Again, I have xn minus 1 here, and I'll have 1 minus alpha x n minus 1 minus 1, which is 1 minus alpha x n minus 2, and so on. So I can just write this forecasted value as a weighted average of my actual observed value of xn and the value that I predicted of xn to be. So remember, if I'm writing xn minus 1 hat one step ahead, it is just representing the forecasted value of xn for me. So now if I have to forecast the one step ahead value from n for my x, what I'm doing is I'm looking at a weighted average of the actual observed value of xn and the forecasted value of xn from using the model that I substituted. So that is how you use exponential smoothing, and it just depends on your forecasted and the actual observed value to predict what's going to happen next to the variable that you have. So again, there are caveats with working using exponential smoothing. So you cannot apply this method if you have a data which has some sort of a trend or some sort of seasonality. So this exponential smoothing that we did is actual, if you use more technical terms, known as single exponential smoothing, because you only have a single parameter here, which is alpha, which is called the smoothing parameter. But there exists other complicated techniques like double exponential smoothing, where you might have almost like 5 parameters. Then you have triple exponential smoothing as well. And the list goes on depending on how you want to vary. And the only thing that stays common is that these weights that you provide to the values of xn and lagged values of xn decrease geometrically. And that is why you have the name exponential smoothing. So I hope that's clear, because this is the end of our learning of how to forecast these time series models. Do you guys have any doubts with this up until now?
No.
Others? What about others?
No, ma'am.
Okay, so I think the next thing that we're going to study is pretty interesting actually. So I think we have already studied, right? If I give you a process, let's say if I give you a process which is, so I have a process xt which is integrated of order 1, and I have another process yt which is of integrated order 0. What do you guys think will be my process xt plus yt? Will it be integrated of order 1 or will it be integrated of order 0? Anyone?
Of order 1.
I think 1.
And why do you think so?
Because when you add it, YT is stationary, but the elements XT is not stationary. So I think as a whole, the process of XT plus YT will not be stationary.
Yeah, that's correct. So remember, when I'm looking at the ARIMA model as well, I have my MA process, which is added to my AR process. And I know that my MA process is always stationary. And if my AR process is integrated of order 1, I know that my AR plus MA process, which will be ARIMA of order 1, of degree of integration 1, right? So if I'm adding a I1 process and another process which is a I0 process, I get something which is a I1 process. So now again, let us say I have xt, which is integrated of order 1, and I have another series yt, which is also integrated of order 1. And now if I ask you, what will be my xt plus yt, what will you guys answer?
Of order 1 itself.
Right? It will again be of order 1, because when you try to remove the orders, you only have to remove the root which is 1. And once you remove that root, let's say if you just difference it, you get a stationary time series. Good. But there is, however, a very important exception to this case, the case right here. So that exception is something that we are going to study now. And like, it's called an exception, but it is something which is widely seen actually in practice as well. especially in economics, I would say. So when I'm talking about the exception, what happens is, let's say if I have a model, so I define a model where my YT depends on XT. So what I'm telling is that my YT model is nothing but something which also depends on XT. So this is the model that I have at hand. And if I say that my ET is an integrated process, so of order 0. So I say that my ET is a white noise process. So what do you guys think? YT minus BXT will follow? So I'll have YT
White
minus
noise.
white noise, right? So with some alpha here, so there will be a trend in the white noise, but I mean, it will still be a white noise, right? Because it has to be a I0 as well. So remember, I know that my YT is I1 and my XT is also I1. But if I assume that my ET is I0, then I know that my YT minus BXT also have to be I0. And whenever such kind of situation happens, you will always know that there will exist only one combination, and this beta is unique. So there will only exist one combination of YT and XT, which will give you something as a stationary process. And that coefficient beta for XT is a unique coefficient. And that is why if at all you have these kind of two series, so I have my YT and I have my XT, which are I1 initially, but there exists some combination of YT and XT, which gives me a stationary process, then these kind of a situation is known, so these kind of time series are known as co-integrated time series. And this was actually proven by an economist, Granger, in year 1981. And he used the help of his associate Newbold, and there is a very famous elementary statistics book by Newbold and Granger. So I think, yeah, this is very interesting concept, and let us see what happens. So maybe I can write the heading here. So we are looking at co-integrated time series. And let us define the co-integrated time series. So remember, starting off, you don't have a process which is a stationary process, because you know that both X and Y are I1 processes. And again, so again, you have to remember that the vector is going to be a non-zero vector, and I'll tell you guys what alpha and beta is in a while. So remember, here when I wrote YT minus beta XT, and if I'm comparing that equation with something like this, what will my alpha and beta be? So if I have alpha X plus beta Y, and these should be stationary. So if I were to compare this alpha X plus beta Y here, I would get my value for alpha as minus of this beta, and beta is the coefficient to Y, which is 1, right? So here there is some confusion with beta, but and that's why I will not keep this here, but you know what I mean. So those alpha and beta is the vector that you care about, and that vector is known as co-integrating vectors. So if I were to figure out this vector, and this vector is known as co-integrating vector. Again, when I'm talking about co-integrating time series, I mean, we know the math behind it, but when do you think this co-integrating time series could be of use? So one of the circumstances would be when two processes are correlated with each another, or maybe there is some another process which correlates with both of the processes xt and yt, and which is why any changes in that variable affects your xt and yt simultaneously. Or it could be the case that maybe my xt depends on yt or yt depends on xt. So the case that we saw here was that my yt depended on xt, and we figured out that something like co-integrating time series is what we can use. Because if you have yt and xt, and if you have both of them separately identified, even though they are dependent on each other, the kind of relation that you will get at the end will turn out to be a spurious correlation. And that is something which has been vastly researched after Granger published this about co-integrated time series. And there were many papers which were found, to just have spurious correlation and no actual relation. So if and only if you have two processes which are integrated of order 1, and you can write them in a linear combination which will give you a stationary time series, then only you can conclude that there must be some relationship between these two variables. So if you have to check whether there is some sort of correlation for some non-stationary time series, then you have to use this sort of a method, which is to employ the fact that these could be co-integrated time series. So let me just walk you through this. And again, if I were to just, describe how would this look in a graph, because we know, so let me just, maybe I can do a little bit something here. So if I have so let's say this is my yt, and this is some time series of yt that I have, and this is some time series xt that I have. And there is some difference. So again, if we look at this series and that series, we see some sort of a trend is going on, and these are clearly not stationary. So these are I1. And what you can do is, if you look at the difference, so this is my yt and this is my xt. But now what I'll do is, I multiply this xt with some beta, and what I get is something like this. So if I get something like this, when I multiply my xt with beta, and then what you will do is, you care about yt minus beta xt. So previously the difference between y and xt was not stable, right? The variance was increasing and decreasing. So it was very low here, but then as and when you increased it, sort of increased as well. But now if you look at this difference, it almost is constant, right? And if you take this time series, right, in between this, you will get that it is indeed a stationary process. So if you subtract this scaled version of xt, and if you remove all the scaling factor, what you are left with is just a stationary time series. So if you were to plot these green plots, I think it would just look something like this. Yeah, just something like stationary. Yeah, and this will be my yt minus beta xt. So I think across time t. So I hope that's clear. And so this is generally observed in economics, actually, from what I know, but I'm sure this must have some applications other than economics as well. So for economics, there is this concept of wealth, income, and consumption. And it is being said that, if you have more wealth, then you're likely to consume more. But there has been some sort of a debate around that concept as well. So I cannot clearly see that, it is a proven fact. But yeah, there is something where wealth and income can be driven by the consumption, or consumption can be driven by the wealth or income that you have. And that's something as well. But the case, so this Granger guy, he was actually awarded with a Nobel Prize in economics, although there doesn't exist an actual Nobel Prize in economics, not the Alfred Nobel that you call. There is some another institution which funds the Nobel Prize in economics. So it's not the actual Nobel Prize that is awarded to other hard sciences, because economics is considered a soft science. So coming back to the co-integrating model, what we have is there is this concept of exchange rates in economics, and I think maybe I can just show you guys. Okay, I think maybe I can just write it here. So if I write a model, something like log of xt is equal to log of pt upon qt plus yt. So here, when I'm talking about xt, this is the exchange rate of dollars and pounds. So this is the dollar upon pound exchange rate, and pt and qt are just the consumer price indices for US and UK. So this represents dollar pound exchange rate, and PT is the consumer price index for US, and this is the CPI for UK. So this is the model that I have, and the exchange rate model is generally, called as something which is an example of a co-integrating model, and it is described by such where your YT is just a AR process. Oh, so it's a ARIMA process. It's a ARIMA 1,1, right? Because you have YT minus 1 and ET minus 1 as well. So this is ARIMA 1,1 where my E's, these are zero mean white noise processes. So this would be one of the examples of co-integrating models where my XT depends on YT. And what you do is, so now again, the variables here are, this is the exchange rate and this YT is something. But what is of concern here is mostly the P and the Q here. So these are the variables that you want to take into, that are of interest, the consumer price indexes, and there is economics behind that which we need not have to concern about. And what you can do is, you will define the model for PT and you will define a model for QT. But now here, because you're looking at logged values, what you will do is you will define a log value. You will define a model for log of PT and for log of QT. And both of them will follow ARIMA 1,0. So they are more likely to be dependent on their lagged values, their own lagged values, and not on the error lagged values. And what you do is, now once you know that log of PT and log of QT follow ARIMA 1,1,0, the logarithm of exchange rate. So again, if I look at my YT, what is my YT? It is just a ARIMA 1,1 process. And now I know that my log of P is ARIMA 1,1,0 and my log of Q is also ARIMA 1,1,0. So if I have to figure out what will be my value, what will be my model for XT. So log of XT here. So I know that my log of XT, I can write this as log of PT minus plus YT, right? And if I know that my YT is a ARIMA 1,1 process, which means it is a stationary process. If I'm assuming that, my value of alpha here is less than 1 in absolute terms, then I'm assuming that my YT is a stationary process. So I know for a fact that log of XT minus log of PT plus log of QT should be a stationary model, which is ARIMA 1,1, right? So that is how you get a co-integrating model where, so if I were to write this, what I have is a co-integrating model with co-integrating vector as, so my x has the coefficient 1, pt has the coefficient -1 and qt has the coefficient 1. So it will have coefficient 1, -1 and 1. And the model which I am describing is log of xt, log of pt, log of qt. So it comprises of these variables where t takes values, so on and on. So yeah. Does this make some sense? I mean, I know it's not that clear. We'll do an example again. Yeah, so let us try and see an example with numerical values, instead of these variables. So maybe I should, yeah. So now let us try to look at an example, a numerical example of how would these things play out in real life. So I'm not going to describe what my xt and yt here is, but let me just write, that my xt depends on xt minus 1 as well as yt minus 1. And there is some error term, of course, pertaining to x. And I have my yt, which again depends on xt minus 1 and yt minus 1. And these etx and ety's, these are independent white noise processes. So these are independent white noise processes. And now I have to prove that these processes, so what I have to do is show that xt and yt are co-integrated with co-integration vector 1 and -1. So if I'm saying that I have a co-integration vector for my xt and yt as 1 and -1, then what kind of a process is going to be stationary process? Anyone? What linear combination I should have for x and y for them to be a stationary process? For it to be a stationary process? If my vector is 1 and -1, anyone?
Sorry, can you repeat your question?
So my question is, let us say if I have two processes, xt and yt, which are not stationary. I know. I mean, I will prove it now, but I'm just assuming that you know that they are not stationary. And you have a co-integrating vector for them as 1, -1. Then what linear combination of xt and yt I have to prove is stationary for them to have a co-integrating factor of 1, -1.
So I think 1 with xt and -1 with yt would help me.
Exactly right.
Yeah.
So I just have to show that
xt minus.
Yeah, so I just have to show that my xt minus yt is indeed a stationary process. But let us see, and I think what we should do is, we should start off with, showing that these processes x and y are both integrated of order 1, because then only we can use the co-integration method, and it is one of the necessary conditions to be able to say that my x and y are co-integrated. So let us try to show that first. So what we can do is, we can rewrite this expression. So maybe I can write this as my expression 1 and this is my expression 2. So I rewrite 1 in terms of yt minus 1. So if I rewrite my first expression in terms of yt minus 1, what will I get? I will have yt minus 1 isolated on my left hand side. And again, I know I'll have to divide all of the expressions that I have here with 0.35. And on the other side, I'll have xt minus 0.65, xt minus 1 and etx. So minus etx, right? And again, what I will do is, I will rewrite this term now for yt. So now I've got this expression. So my second step will be to write this for yt. So now instead of t minus 1, you just substitute t here. So what will you get? The constants will remain constant. Just instead of t, now you will have t plus 1. Right? Because instead of t minus 1, I have substituted t. So I'm just trying to take one time step ahead. So t will become t plus 1. T minus 1 will become t. And again here t will become t plus 1. And now what I will do is, with these values of yt minus 1 and yt, I will substitute this in my second expression. And now I know that I have yt minus 1 and yt in terms of x's. There is no y here, right? So if I substitute this yt minus 1 and yt here, I will get an expression which consists of only xt, x's, right? So what I will have is, and I don't care about this being, the error term related to y or x, because at the end, what is it? It is just white noise and it doesn't affect my stationarity, right? And that is what I'm looking for. So the next big step will be to substitute the values of yt and yt minus 1 derived above in second expression. So if I do that, what will I get? I will have to rewrite this as it is here. Now 0.35 xt minus 1 will be as it is. And again, here I'll substitute my value for yt minus 1. And the other term for yt as it is. So this will be the expression that I have. And if you solve for this and if you accumulate the common terms xt and xt minus 1 everywhere, so what you will end up with is, and I think we should all try to solve for this, just arithmetic. So what you will end up with is something like this. So you will have xt plus 1. Yeah. So you will have xt plus 1 as 1.3 xt minus so this is what you will get. But again, we can again work with this expression, but it's just easier for us to, convert it in something like xt equal to. So I'll just take one time step backwards to each and every variable that I have. Right? And now if you try to figure out, so these error terms won't matter, right? Because they are Markov and it's always stationary. So what you have to care about is this part, which is the AR part. So the characteristic, what will be my characteristic equation here? Anyone? Anyone? What will be my characteristic polynomial here? So I'll only have to take into consideration these variables, right? What do you guys think will be my characteristic equation here?
Yes, that will be the characteristic equation, no? 1.3
Yeah.
xt minus 1.3 xt minus 1.
Wait, what? 1.3
If
xt
you
minus?
take minus 0.3 that side, it will become 1.3
Yeah.
xt. And
Oh,
minus
so I
1.
have 1. Yeah. So I have 1.3 xt minus 1. So it will be minus 1.3 xt minus 1.
Yeah.
Yeah. Okay. Anyone else want to try? So just give me my characteristic polynomial. It should be in terms of either lambdas or z's, not in terms of x.
Ma'am, the above equation is the x
And
0.3.
the third term should be 0.3 xt minus 2.
Wait, what should it be? It should be 0.3 xt minus 2. Oh.
Yes.
Okay. So I see. I think, wait. Wow, I'm so bad at even copying. I have 1.3 xt here, and I have minus 0.3 xt minus 1. So, yeah, it should be xt minus 2. Thank you. Okay, so what will be my characteristic polynomial now?
0.3 lambda square minus 1.3 lambda plus 1.
Right. So it will be 0.3 lambda square. I want to write this now. So it's going to be 0.3 lambda square minus 1.3 lambda plus 1. And if you try to figure out its roots, what you will get is, so one of the lambdas will be 10 upon 3 and the other lambda will be 1. And now you know that this clearly is not a stationary process.
Yeah.
Can you mute yourself? No, thank you. So what we have here is a lambda 2 which is equal to 1. And we want all of the roots to be more than 1 in absolute terms. And if you difference the series 1, this root will go away. And what you will be left with is only 10 upon 3, which will be what? A root which is greater than 1 in absolute terms. And then the process will be stationary. So again, you can use this method to prove that, this is indeed a stationary process once you difference it. But again, there is another method that you can use. So you can actually, try to figure out what happens if you take a difference of this series. And if you do that, what you will get is, so this is just another method. So because you know that, you're looking at co-integrating vector, you know that they are going to be integrated with other one. So you don't have to difference it twice. So you can just write it as nabla xt plus 1, and I'm just writing the direct answer here. And again, you can, just figure out the characteristic equation of this differenced process later on. So there are two different ways you can determine the order of this process. And again, as we know that 0.3 in absolute terms is less than 1. So I'm looking at here, which is why I want it to be less than 1. The process is clearly I0. And so all of this implies that my xt is a I1 process. And using the similar concept, you can say that, using the similar derivation, or you can just write as well, I guess, similarly, xt is also going to be a process which is integrated of, yt is also going to be a process which is integrated of order 1, because these actually, they have similar structure. It's just that the coefficients are different. And if you try to solve, you will again get some sort of the same answer for that. Okay, so now the very first condition is satisfied that my xt and my yt are a I1 process, which says that they aren't stationary. But now let's see if there is any connection between those. So now we have to prove that they are co-integrated with the vector 1 comma minus 1. So let us try to see what happens to our series if you do that. So my series becomes x t minus yt, right? And if you do xt minus yt, what you will get is 0.3 xt minus 1 and blah blah blah. So if I rewrite my xt minus yt using all those expressions there, what I will get is 0.3 xt minus 1 minus 0.3 yt minus 1 plus etx minus ety, right? And what I can do now is, so remember the process that I have to show is a stationary process is my xt minus yt here. So let me define this xt minus yt as wt. So what I have to show is that this is a stationary process. So what I can do is, now I can rewrite this again as xt minus yt being equal to 0.3. I can take it out as common, and what I'll have is xt minus 1 minus yt minus 1, right? So I'll have xt minus 1 and yt minus 1, and what I can do is now substitute for xt minus yt as wt. So if I do that, instead of xt minus yt, I can write wt, and instead of xt minus 1 yt minus 1, I can write wt minus 1. So I know that my wt is indeed just a AR process, and it only depends on one lagged value of wt. So this is nothing but, I can conclude that my wt is a AR1 process. And to check whether if it's a stationary or not, I know that 0.3 here is in absolute terms less than 1. Thus, wt is a stationary process. Which is I0. So what we have just proven is that there exists some linear combination of x and y which will give me a stationary process. And this is only possible, remember, this is unique. So this 1 and minus 1 is unique. And actually this 1 and minus 1 is not unique, but the coefficient here. So there's one more thing which I need to see probably. So if I have something like 3 and minus 3 as well as co-integrating vector, so even this would satisfy the same conditions. So again, remember, whatever co-integrating vector you have, if you scale those up, if you scale that vector up by any constant k, it will still hold the same properties. So again, when I'm saying that it is unique, I mean that the division, the relativity, the relative weights is unique always. So it will be 1 and minus 1, or let's say if I have the coefficient for x as minus 1, then my coefficient of y will be 1. So it just have to have the same relationship. That's it. I hope that's clear. Does anyone have any doubts with this?
No.
No.
What about others?
No.
Okay,
I just
so
have
this was
one.
a, yeah.
If it's more than one, will it be stationary?
Can you say that again, Sahil?
what if the value is more than 1? Will it be stationary? Like if it wasn't 0.3.
Yeah, it
Something.
wouldn't be stationary, right? It wouldn't be stationary.
Cool.
And so first of all, you wouldn't get a value here which is greater than 1 because you are supposed to show that this co-integrating vector satisfies. So you kind of know that, the expression that I'm going to get for WT has to be a stationary one. But if that was not the case and you were supposed to check whether 1 comma minus 1 is a co-integrating vector, and if you would have, something like 1.2 here, then of course this wouldn't be a stationary. And you would say that, xt and yt aren't co-integrated time series. So yeah, perfect. Any other doubt, anyone? So now actually I will just show you guys some other models which are non-linear. So some of them are non-linear and some of them are non-stationary models, which are quite interesting models actually. Let me just share my screen. So yeah, the models that we have yet studied, we assume that, all of those are stationary and are linear in a way. But now let's see what happens or what possibilities can there be exist, apart from the ones that we have just studied. So the very first model you have here is something called as bilinear model. And why is it known as bilinear? So it clearly has to do something with 2 and something with linearity as well. So what happens is this expression here is, just a function of 2 variables. So here you only have 2 variables, which is like x and e, right? And what you do is independently, this expression is linear in both the variables. So when I say that, what it means is if I assume that I know the values of x, then I see that my p's are linear, right? So they don't have any square and anything. And if I ignore the values of a and if I look at my values of x, I know that these are also linear in terms. So I see that this is a bilinear model and you can have more than 2 variables where, they would be independently linear with each of those in respect to each of those. But again, the very important aspect here in this model is here. So if you see, my xn minus 1 gets multiplied with an minus 1 here. And these kind of a model, so this kind of a thing, and it's known as actually boosty behavior. So what it means is that if you have a process which is far away from the mean, then there will be just, some fluctuations which will tend to be of a higher value than what you would observe in the normal case. And the similar thing goes with the error term as well. But yeah, if you want to capture any kind of a relationship like this, you have to use a bilinear model. So this was just one of the models. And the next model, I think this is one of the models which is highly used not only in economics or finance, but also in psychology, medicine, biology as well. So in short, this is known as TAR model. So this is a threshold autoregressive model. So remember the autoregressive models, the simple autoregressive models which we studied had something like situation where the xn dependent on its own lagged value. But now when I'm talking about the threshold autoregressive model, what happens is the process is likely to behave differently when the value of the variable exceeds a certain threshold. So for this example, they have defined the threshold as D here. And what they are saying is that the xn, that the coefficient for xn minus 1 here, if my xn minus 1 is less than or equal to d, is alpha 1. But if it is greater than d, then it is alpha 2. So this, and again, so here I think they have used the same equation for the case where it exceeds the threshold value, but it need not be the case. You can have a AR1 model here and you can have a AR2 or 3 model here. So it depends actually on what kind of a process you are looking at. And again, just to provide you guys with an example of where this model is used. So in generally, if you look at, the drug case, so if you take a drug in lower thresholds, in lower quantity, which is, below a certain threshold, the toxicity of the drug, which is measured using this equation. So let's say my XN measures the toxicity of the drug, how harmful the drug can be. So if taken within the limits, it could prove to be, less harmful. But if taken more than the certain threshold, it could prove to be more toxic. So the expressions would have to differ. And that is what the case is in threshold autoregressive model. And I think the other case that you can use is in biology, where let's say if you're studying the population of the animals that you have in a biodiverse area, what you will see is the population increases slowly. So till my xn minus 1 takes a value d, the population is increasing, but at certain point, my xn minus 1 is equal to d. And what happens is now it has started increasing, and it goes beyond d. So what happens is once you have a certain number of animal population, which is beyond a threshold, it can lead to, the decrease in the total population because of the competition and the limited food that they might have within an area that they are, reproducing. So this model can actually be used there as well. And this is actually a very nice model, which is sometimes used to fit the nonlinear data. And yeah, so this is actually the TAR model. And what happens is in the actual survival population model, we also have something like alpha 1 minus alpha, where you get a graph, something like this, for the population. That's, so we don't have that model because that is an actual nonlinear model, and it has a very interesting video. Actually, I might put that video in the Google Classroom. So again, they are saying that, in the extreme case, you might just set this to 0, where until and unless your xn minus 1 takes a value d, you have some value for xn, but if it goes beyond d, it will take the value en, which is just basically random white noise. So, okay. The next kind of model that you might have is a random coefficient autoregressive model. This is actually a very crazy model, which is not generally used. But let's say if you just want to focus on one single property within a data set, then you might resort to use this. And again, I tried to look up something about this, but the literature is just much vast and confusing. And we don't have to, worry about this model, but just know that this kind of models also exist. So when I'm talking about a random coefficient autoregressive model, what happens is my coefficient can be any one of these. So my alpha t here can be either alpha 1, alpha 2, alpha n. So I have a sequence of independent random variables where I can take any coefficient that I want. And sometimes this is, used to represent the behavior of an investment fund, where you just assume the mean as 0, or you can always, subtract the mean from the process to make it a mean 0 process, and then say that your alpha t is just 1 plus it, where it is the random rate of return. So the rate of returns will, of course, depend and vary across all the other kind of variables that you have. So let's say if you have stocks, bonds, and T-bills and all of those sort of stuff, so your rate of return will vary, and thus you can have different values for IT, but yeah, I don't know in particular where they can use this model apart from the one that they have mentioned here. Okay, so the next kind of model that we have is arch models. This is known as autoregressive with conditional heteroscedasticity. So can someone explain me what do they understand by the term heteroscedasticity? Anyone? What do you understand when I say, that there is heteroscedasticity in my data? What's happening in the data? Anyone? Come on, I think everyone should know about heteroscedasticity. I think I have discussed heteroscedasticity previously as well, sometime in some lecture. Not even a single person knows what is heteroscedasticity. Do you guys know what is homoscedasticity? I think if I'll tell you guys what is heteroscedasticity, you guys will be like, oh, is this called heteroscedasticity? We knew this concept. But just not the fact that it is called heteroscedasticity. So, okay, let me just break it to you guys. So when I'm talking about heteroscedasticity, what I mean is that my variance is not constant over time. So I have some series xt, which is something like this. So you see, as and when I increase the time, the variance between the data is increasing in nature. And that would be heteroscedasticity. So if I were to plot, let's say, some data which is like this. So this is mostly homoscedastic, right? Because the interval of the variance is kind of constant throughout the time. But here it is not. It is clearly increasing as and when I increase, as and when I go ahead in the time. So this kind of data set is said to be, a heteroscedastic data where my variance is not constant. So hetero is for different. So you have different variance which actually depends upon the time. So again, when your data has such kind of time varying volatility, you cannot use AR or MA models. But what you can do is you can use arch models. So there are another kind of models known as Garch models, Sarch model, and there is like a family of arch models, but this is just the basic one. And they have defined here what kind of a model it is. So yeah, again here they have defined, homoscedastic and heteroscedastic. So different variants, which we just saw. And this is actually generally seen in financial data of returns or the prices. And if you look at the price data, it is heteroscedastic. And that is the reason why you look at the difference and the log of the prices data, and which will give you the return data, the data of the returns on any stock, which is generally the homoscedastic data. And it's very easy, to work with homoscedastic data. And it's also shown that the returns are stationary. And again, it's easier to work with stationary data than with something which has some sort of a trend. Because if you look at the price data, it will of course have some sort of a trend or a downward trend, something like that. So this is just how they have defined the models. And again, you see some squares here and some alpha k. So here you have P, right? So this is an arch of order P, because my xt here depends on pth lagged values of x. So xt minus 1, xt minus 2 till xt minus P. And this is just the another model which you can use. And yeah, again they have just, I think, yeah, so here they are talking about, you know, the return and the price data. So yeah, Arch model can also be used for the daily return data. And yeah, that's it. So I think this is where my chapter ends for time series. And in the appendix, they have just showed us, you know, how to figure out the eigenvalues. But I think you guys already are aware of how to do that. So maybe now what I can do is, we can solve a question. Yeah, so if you have a look at this graph, you have a ACF and you have a PCF. So you can see that ACF here cuts off after lag 1, and my PCF continues to geometrically decline, right, as and when I increase my value for lag. So what kind of a model do you think this is going to be? Anyone? Is this AR, MA, or what kind of a model? So my ACF has, you know, directly cut off after the lag 1.
MA.
MA with lag. What will be the lag for MA?
1.
1, right? Because after 1, the value of ACF is just 0. So yeah, these kind of questions will likely come up in the exam, and then, oh, they have actually used the word Yule-Walker. So when I'm talking about Yule-Walker equations, what do they mean by Yule-Walker equations is actually very simple, just the covariance equations. So remember the equations where we used to determine the value of gamma 0, gamma 1, gamma 2 in terms of each other. So this would be some number, let's say, or this would be some value, and then you will have gamma 0 plus something. Here you will have gamma 1 plus gamma 0 and some number here. So these will be the Yule-Walker equations. That's it, nothing else. So that's just a fancy name. And so they have just asked you to derive Yule-Walker equations for this model here, and then, yeah, explain whether if this is going to be a 0 or not. So I think this is okay. Yeah, and again, state the 3 main stages in the Box-Jenkins approach to fitting an ARIMA time series. I think you all must be already aware of this 3 main stages, and this is just a theoretical. I would say you guys should try this question. This is actually a very easy question of, I guess, turning point test. Yeah. But maybe what we can do is, we can do this question in the class. Let us do this. So I have this question. I want you all to, you know, take your time and figure out the answer for one. First part. I think it shouldn't take you more than half a minute. So I have some values for ACF and I have some values for PACF. This is somewhere near to 1 and this is somewhere near to 0. So yeah.
AR model.
With what lag?
Lag 1. No, 2.
1. 2, right? Why do you think it's 2? Because my PACF after lag 2 is almost close to 0, right? It is 0.085, which is almost 0. So I can easily see that my model that I'm looking at is AR with lag value 2. Okay, that was very easy. So the next question is, you consider the AR1 model. So what you're doing is, you're considering this AR1 model, which is YT as alpha 1, YT minus 1 plus AT. And it is just a white noise error term with mean 0 again and variance sigma square. So what they're asking you to do is, calculate the method of moments estimates for the parameters alpha 1 and sigma square that you have here on the basis of observed sample. Okay. So we already know that this is actually, a better AR2 model, but that they are asking again later. So what we are supposed to do here is just ignore these values and assume that, this is this is the values given to us for this model here. And on the basis of these values, you have to figure out the estimates for alpha 1 and sigma square here. So what do you guys think you should do? Anyone? What do you guys think you should do to figure out the value of sigma square and alpha 1?
Find the covariance.
Right? So can you do that? So I want you all to, solve this question and try to figure out the value of different covariances at different lags and try to see if you can come up with the values of alpha 1 and sigma square. Let me know once you have the answer, or if you have any doubts, you can ask. Anyone got the answer yet?
And
A1
to
is
calculate covariance between
0.854.
ET and
YT minus 1, shall I write ET as YT minus alpha YT minus 1?
no, you can just expand the expression for yt minus 1 and see whether you have ET in that expression or not.
Okay.
Yeah. So this kind of clarity you will get once you solve more and more questions. So you will know what and where to expand and where to not.
I'm not sure if it is right, but I'm getting A1 as 1.
You're getting A1 as 1. So how did you derive that value of for 1?
I'm getting the second equation as gamma 1 is equal to A1 gamma 1.
A1 gamma 1. Check whether it's gamma 1 or not. I think it should be something
It's
other than
gamma
gamma 1.
Gamma
naught.
0.
Gamma naught.
Right? It should be gamma 0.
Yeah,
For
correct.
yourself, I think, yeah, it should be gamma 0, right? So now determine what's going to be the value for alpha 1.
Alpha
Alpha 1 is
should be
0.845.
0.854.
Yeah, it should be the 1. It should be 0.854, which is just my first value for the PACF for lab 1, right? Correct. And now if you were to determine the value for sigma square, how will you determine the value for sigma square?
So we have the sample variance over here, which is 1.253. So we'll just find variance of yt, which we'll get as A1 variance of yt minus 1 plus sigma square, and then just replace the value of 1.253 there, and with A1 we just put 0.854.
Yeah.
After finding gamma 1, we'll find rho 1 with just dividing it, and then find sigma square up from that.
Yeah, that should be it. So did anyone try the whole process?
I'm getting the sigma square value as 0.1709.
I think there's some mistake. So what was the value for what was the expression for the variance you got for gamma 0? What did you get for gamma 0?
Gamma 0 is equal to A1 square gamma 1 plus sigma square.
Oh, so just check whether it's A1 square or just A1, because it should be just A1, right? You only have A1 yt minus 1, and on the other side, you will have only yt, right? So it should be A1, y1, A1 gamma 1. It is the covariance of A1 yt minus 1 and yt, right? So if it were variance of A1 yt minus 1, then it would have been A1 square gamma 0. But now, if you want to write it as gamma 1, then its coefficient is going to just be A1, right? Try to check once again.
Sigma square is 3392.3392.
Yeah. Yeah, that's the correct answer. So maybe I can solve on the board. Let us see. So first of all, what I will do is I will figure out my value for gamma 1 using covariance of yt and yt minus 1. And the answer that I'm going to get is I'll substitute for yt here, this expression, and the answer I'm going to get is sigma square, because my et is, the answer is going to be A1 gamma 0. So it's going to be A1 gamma 0, which will just imply that my gamma 1 upon gamma 0, which is nothing but rho 1, is the value for A1. So this implies that my A1 is 0.854, right? And if I now have to figure out, and again, this is my calculated value, so I have to write a hat over there. And now what I will do is I'll consider the lag 0. So covariance of yt comma yt, and this will be covariance of A1 yt minus 1 plus et comma yt. So remember, whenever they ask you to derive Euler-Walker equations, what you have to do is derive gamma 0 in terms of gamma 1. So now you have covariance of A1 yt minus 1 comma yt. That will be A1 gamma 1, and et and yt is just, you don't know as yet, right? So let us derive. So covariance of et comma yt. So instead of yt, I'm going to substitute this expression, which is A1 yt minus 1 plus et.
It will be sigma square, right?
Yeah, so I'm deriving the covariance that I will have here, and it will just be sigma square. Correct. So that's it. And now what you will have is, you have the estimates for gamma 0 already. So gamma 0 is given to you as here. So it's in somewhere. It's in this 1.253, right? This is the value for gamma 0. And if you substitute this value for gamma 0 here, and you know the value of rho 1, you get the value for gamma 1. And that's how you can derive the value for gamma 1 hat, which will just be 0.854 times 1.253. And once you derive the value for gamma 1 hat, you now know the values for gamma 0 and gamma 1 and A1. And you also have this relationship, which is like, you know, that my gamma 0 is equal to A1 gamma 1 plus sigma square. I know gamma 1, I know A1, I know gamma 0. So I can rearrange and derive my value for sigma square, and you will get the value for sigma square as 0.3392. So is this clear to everyone?
Yeah.
Yes.
Anyone has any doubts with this? So again, for someone who is, wondering what will be the correlation between AT and YT minus 1. So if you substitute the equation for YT minus 1, you will have A1 YT minus 2 plus ET minus 1. And you know that ET minus 1 or YT minus 2, any one of those is not related with ET. So if you want to figure out for YT minus 1, you will easily see that it will have ET minus 2 and so on. So none of the YTs beyond YT are going to be correlated with ET, including YT minus 1. So yeah, I hope that's clear to everyone. So I'll just clear it. Okay, so that was it for the part 2. And again in part 3, now what they're asking is to consider the AR2 model. They're blah, blah, blah about ET and the variance, sigma square, And now they have asked you to derive the estimates for the parameters I1, A2, and sigma square. So again, you will have to derive the covariance functions like we just did. So maybe I could leave that up to you guys. So I think this is going to be a good exercise. Just don't get bogged down with, so many variables involved. Try to be persistent. And so do you guys want me to solve this in the lecture now, or do you guys think that you can do this on your own? Anyone? If you would like me to
do
solve,
this.
we will do this. Anyone else? If you want me to solve, I can solve it. So we can actually solve together as well. Okay, so maybe what I can do is, instead of solving, I can just walk you guys through this solution. And you guys can actually solve it by yourself as well. But just in case. Yeah. Yeah, so it's here, right? So if I'm looking at the gamma 1, so let's say here we are starting off with gamma 1. I'm looking at the covariance between yt and yt minus 1, right? And again, I know that, I should have a look at yt minus 1 instead of yt plus 1, because that is the case which is much more relevant to what model I have. So if I expand my yt here and I leave my yt minus 1 as it is, I get alpha 1 and yt minus 1, so gamma 0. And with alpha 2, you have gamma 1. And with et and yt minus 1, it's not correlated, so it's just 0. And again, if you divide this by gamma 0, gamma 0, gamma 0 everywhere, you get this relationship here, because this will just become 1. And here you will have gamma 1 upon gamma 0, which is the same here. So you will take this over there and you will have 1 minus alpha 2, 1 minus a2, and your rho 1 is just this. And the next autocovariance you consider with lag 2 when you get some expression like this. So what you will get is the value for rho 2, let's say here. And now what you can do is you can just substitute the values for rho 1 and rho 2 from the observed values which were given in the question and solve for this A1 and A2, because this is like two simultaneous equations with two unknowns. So A1 and A2, you can easily derive the values of A2 here, and then you get the value for A1 as well. So now remains is the value for sigma square. So you can take the covariance of yt comma yt, which is gamma 0, to derive this expression, and you know the value for gamma 1, gamma 2, and gamma 0, which can be derived easily because you are given the value of gamma 0, and you know the value of rho 1 and rho 2 as well. So you get the value for gamma 1 hat and gamma 2 hat. And you can rearrange the expression while substituting the values of alpha A1 and A2, which you just derived earlier, to figure out the value for sigma square. And the fourth question just asks you, to list some statistical tests that you can apply to the residuals once you fit a time series model. So this forms part of the diagnostic check of the model that you have fitted, whether it's a correct model or not, or is there some relationship which is still, there, which you can exploit and put a variable to. So one of these you can mention. So they have asked you for 2. So if you mention any of these 2, it would give you the equal points, irrespective of how complex the procedure is. So turning points test, you can inspect the graph of the residuals, or you can use portmanteau or arc box test. So anything out of these 3 would suffice. Was this clear to everyone?
Yes.
Any more doubts
Yes,
in this? So I think once you all, try more questions. So I think someone already has shared the revision notes, but I will still again share the revision notes and upload them on the Google Classroom as well for you guys to have it handy, and maybe on the drive as well. So yeah. I think that's it from my side. So I just hope that you all enjoyed my teaching. And let me just stop the recording now.